The explain plan results let you determine whether the optimizer selects a particular execution plan, such as nested loops join. It also helps you to understand the optimizer decisions, such as why the optimizer chose a nested loops join instead of a hash join, and lets you understand the performance of a query. A statement's execution plan is the sequence of operations Oracle performs to run the statement. The row source tree is the core of the execution plan. It shows the following information and ordering of the tables referenced by the statement. An access method for each table mentioned in the statement. The explain plan statement displays execution plans chosen by the Oracle optimizer for select, update, insert, and delete statements. A statement's execution plan is the sequence of operations Oracle performs to run the statement. The difference is the explain plan is what the optimizer thinks will happen when you run, the execution plan is actually happened when you ran the query. You can execute the explain plan for command in any development environment or SQL Plus by running explain plan for select from dual. It will, however, not show the plan but save it into a table named plan_table. To display the last plan that was explained in the current database session, select from table, dbms_plan.display. Start SQL Plus or SQL Developer and log into the session in which you explained the plan. Explain plan for select from table where. Query plan_table using dbms_xplan.display. Specify the query as follows. Select plan_table_output from table dbms_xplan.display. Alternatively, specify the statement ID using the statement_ID parameter. Select plan_table_output from table dbms_xplan.display, statement_ID equals statement_ID. Select plan_table_output from table dbms_xplan.display, null, x_plan2, basic. Select from table dbms_plan.display or SQL_ID. A format option that determines the level of detail, basic, serial, typical, all, and in some cases adaptive. Select from table dbms_xplan.display_cursor, SQL_ID equals dqkxjrqwyrzqj. Format equals ALLSTATS LAST plus cost plus bytes. To see the results of adaptive optimization, select from table dbms_xplan.display_cursor, format equals plus ALLSTATS. An explain plan is a tree. The database uses depth-first search to traverse it. This starts from the select operation at the top of the plan, then travels down to the topmost leaf. After reading the data from this source, it goes back up to its parent.at. This point, the process repeats. Travel down the plan to find the next unvisited leaf. After reading this, pass the rows back up to its parent. In the serial case, the best driving table produces the fewest numbers of rows after applying limiting conditions. The database joins a small number of rows to larger tables using non-unique indexes. The goal is to minimize logical I/O, which typically minimizes other critical resources including physical I/O and CPU time. The row source tree is the core of the execution plan. The tree shows the following information. The join order of the tables referenced by the statement. An access path for each table mentioned in the statement. A join method for tables affected by join operations in the statement. Data operations like filter, sort, or aggregation. In addition to the row source tree, the plan table contains information about the following. Optimization, such as the cost and cardinality of each operation. Partitioning, such as the set of accessed partitions. Parallel execution, such as the distribution method of join inputs. Some factors that affect the costs include the following. Data volume and statistics. Bind variable types and values. Initialization parameters set globally or at session level. Explain plan output shows how the database would have run the SQL statement when the statement was explained. Because of differences in the execution environment and explain plan environment, the explain plan can differ from the actual plan used during statement execution. Execution plans can and do change as the underlying optimizer inputs change. SQL tuning is all about cardinality. If cardinality estimates are wrong, queries will not perform well. In the preceding plan, employees is the outer row source and departments is the inner row source. The optimizer chooses to access employees using an index scan and departments using a full scan. The optimizer chooses a nested loops join. The optimizer filters on last names that begin with T and matches on department_ID. Here's another example. The order of operations in this plan is: start from the top of the plan, select statement, and go down to the first leaf. This is the table access full of the covers table in execution plan step 4. Pass the rows from this table up to the first leaf's parent, which is the hash join in step 3. Find the next unvisited child, which is the table access full of the blankets table in step 5. Pass the rows to the hash join in step 3. Step 3 has no more children, so return the rows that survive the hash join in step 3 to the hash join in step 2. Search for the next child of step 2. This is the table access full of the sheets table in step 6. Pass these rows to the hash join in step 2. Step 2 has no more children, so return the rows that survive the hash join in step 2 to the hash join in step 1. Repeat the process until you've run all the operations. So the complete order for accessing the execution plan step IDs is 4, 3, 5, 3, 2, 6, 2, 1, 7, 1, and 0. Here's another example. This uses the same 4 tables as the previous query, but accesses them in a different way. Here the order of operations is: travel down the plan to the first leaf. This is the table access full of the bagpack table in step 3. Pass the rows from this table up to the first leaf's parent, the hash join in step 2. Find the next leaf, which is the table access full of the books table in step 6. Its parent is a multi-child operation UnionAll, so the database will next execute steps 7 and 8. There is an optimization, concurrent execution of UnionAll, that means that the database can run all of these table scans at the same time in parallel queries. Pass the rows from the tables at steps 6, 7, and 8 up to the UnionAll in step 5. This step combines the rows into one dataset. Work back up the tree to the hash join in step 2. Join the rows from steps 3 and 5, passing the surviving rows up to the hash group by in step 1. Finally, return the data to the client. Tuning a parallel query begins much like a non-parallel query tuning exercise by choosing the driving table. However, the rules governing the choice are different. For parallel queries, the driving table is usually the largest table. It would not be efficient to use parallel query in this case because only a few rows from each table are accessed. Parallel operations include the following: parallel_to_parallel, parallel_to_serial. A parallel_to_serial operation is always the step that occurs when the query coordinator consumes rows from a parallel operation. Another type of operation that does not occur in this query is a serial operation. If these types of operations occur, then consider making them parallel operations to improve performance because they too are potential bottlenecks. Parallel_from_serial. Parallel_to_parallel. If the workloads in each step are relatively equivalent, then the parallel_to_parallel operations generally produce the best performance. Parallel_combined_with_child. Parallel_combined_with_parent. A parallel_combined_with_parent operation occurs when the database performs the step simultaneously with the parent step. If a parallel step produces many rows, then the QC may not be able to consume the rows as fast as they are produced. Little can be done to improve this situation. When using explain plan with parallel queries, the database compiles and executes one parallel plan. This plan is derived from the serial plan by allocating row sources specific to the parallel support in the QC plan. The table Q row sources, pxSend and pxReceive, the granule iterator, and buffer sorts, required by the two parallel execution server set PQ model, are directly inserted into the parallel plan. This plan is the same plan for all parallel execution servers when executed in parallel or for the QC when executed serially. The following example illustrates an explain plan for a parallel query. One set of parallel execution servers scans EMP2 in parallel, while the second set performs the aggregation for the group by operation. The PX block iterator row source represents the splitting up of the table EMP2 into pieces to divide the scan workload between the parallel execution servers. The PX send and PX receive row sources represent the pipe that connects the two sets of parallel execution servers as rows flow up from the parallel scan, get repartitioned through the hash table queue, and then read by and aggregated on the top set. The PX send QC row source represents the aggregated values being sent to the QC in random, RAND, order. The PX coordinator row source represents the QC or query coordinator which controls and schedules the parallel plan appearing below it in the plan tree.